All right, welcome back everybody for the last talk of the day. So we're very happy to have Ahmad Beirami, who's a research scientist at Google DeepMind. Ahmad has been doing a lot of very exciting work in sort of the safety and alignment space, and he's kind of my go-to person if I'm trying to understand like terminology that I really don't want to deal with. He's kind of very good at explaining in a theory-friendly way what's going on. Before Google, he was at Meta, and before Meta, he was jointly a postdoc at MIT and Harvard, and his kind of background is kind of in some union of information theory and machine learning, and today he'll tell us about alignment.
Yeah, thank you so much for the very kind introduction and invitation. And thank you all for showing up for the last session of the day. I'm sleepy myself, so hopefully I won't make you sleep. So if you're here for principled kind of reinforcement learning theory, like the first talk of the afternoon, you're going to be disappointed. If you're also here for impressive RLHF algorithms with impressive chatbots, you're going to also be disappointed like the second talk. So this is going to be hopefully very simple. And it's going to be rooted in safety alignment. So some of the issues that we kind of encounter when we're doing safety alignment are a bit different from general RLHF methods when you have like clean rewards. So maybe we can get started. So basically, I think alignment, so I don't need to go through this slide. I think this is like by now, everybody talked about it. But generally, I just want to just mention a few words that we're going to be thinking about more of the HCI issues that come with respect to alignment and the actual human preferences. And these are going to be nuanced, noisy, and so I think that's kind of going to be the gist of the talk. So to set the problem up, maybe we can start with an example. So what do we mean by alignment? We're going to prompt a language model and ask for a joke, and the language model is going to generate a joke. And by alignment, we in this context, I mean, we don't want the joke to have any racism, any stereotyping, any profanity, and things of that sort, which could be potentially hard to validate. And we may also have adversarial users, and so maybe somebody is coming and asking, tell me how to make a bomb. And in this case, we don't want to also generate kind of any harmful instructions. I think Ahmad talked about this example and like adversarial robustness quite a bit. And so we want to make models kind of more safe through what's called alignment. Okay, so today we're going to try to understand this alignment process through a simplified lens. I think a lot of the context was already covered by the first two talks, so that's going to be good for me. We're going to talk about a simple inference-time alignment framework called control decoding, and I'm going to show why this is like an interesting and kind of solution for alignment purposes. We're also going to talk about a very simple algorithm for alignment called best of n, where you're generating n responses and then picking the best one. And we're going to try to understand why it works so well. And just in the end, I will try to talk about some practical issues that we have with safety alignment. Please stop me if you have questions. So this hopefully should be an interactive talk. Okay, so what is alignment? We start with the generative language model. So in this case, I'm going to be using P throughout this talk to define a language model. Language model gets a prompt, X, and it's going to define a distribution over all possible responses and to be able to generate an outcome Y. We think about a reward model in this context, R. I'm going to think about reward to be the log likelihood of another generative model, which I call the alignment language model, Q. So R is just log of Q. Okay, so to be able to make it unique and get rid of the kind of the constant that you could add. And we usually think about expected reward. So expected reward in this case, for the way I defined it as log of Q, when we write down expected reward, is just going to be a cross entropy, negative cross entropy between P and Q. And generally, the goal of alignment is to sample from a different distribution pi, which I'm going to call a line distribution, that improves expected reward. So we want to increase expected reward, but we want to perturb little from P. So we want to remain close to P. And so we're going to try to formalize this notion. Okay, so yes.
Alignment language model. Is this something that you have or you want to reach?
No, yeah, it's just basically a change of notation. So you can, for any R, you can define Q. It's just exponentiate R and you get Q, and I will tell you why I like it. So from an information theory perspective, I like cross entropy, and I think it has some connections with other kind of quantities in information theory. That's why I'd like to define it this way. Okay, so let's start with a very simple baseline for alignment. It's called best event. So what is best event? I'm going to use my language model P. I'm going to draw n responses IID from the language model. And then I'm going to just look at them, basically rank them based on the reward, and then pick the best one, and I'm going to serve that to the user. So implicitly, I'm defining a new distribution pi n from which I'm sampling, and that's going to be the best of n distribution. Okay? Now, this is extremely simple. There's no training happening, except training the reward model. But from an alignment perspective, it's as simple as it gets. I'm going to try to convince you today that it's extremely effective. But it's just extremely expensive in terms of throughput. You can't really serve it to the user. It's also incompatible with streaming, because one thing that I didn't talk about is that language models are autoregressive, so they generate responses token by token. So far, we have not seen anything that resembles a token. We have been talking about language models as distributions over entire responses. But what that means is that now you have to actually generate all these responses, go all the way to the end. Like if the prompt is generate a book, you have to generate n books, and then you start looking at the books and see which one is better, and then start serving it to the user. Whereas generally, we want to be able to start serving tokens quickly as we keep generating, because there is latency associated with basically generating every token. Okay?
So why is it actually so bad in terms of throughput? Can you not just generate the n things in parallel or something? And
yes, but so that's basically the why. Because generally, let's say I have n GPUs, or n is overlaid m GPUs. Now, if I'm using all of them to serve one user, then the number of users I can serve is going to be impacted, right? So basically, a number of users served is going to be impacted by a factor of n.
So in this process right now, there's like, are we using any specific function to calculate the distance between distributions, like in general when empirically measuring?
So here, I didn't even tell you what the distance between this distribution and the base distribution is, and we're going to talk about that as well.
Okay.
Right.
Thank you.
So like, this is like if I had the NIID drawn from P, and then I am trying to so instead of just drawing from P, if you're trying to draw from P with some towards R, or like e to the power R, then this thing of like being close, instead of drawing from
Yeah, you can make it better, right? Is that what you imply?
That reduce the kind of some of the.
Yes, yes, definitely, yes, absolutely. But we are going to also define, like, come up with other ideas of actually helping with remedying and trying to keep it low. Okay. So in practice, so given that we can't really deal with best of n. In practice, we usually do KL-regularized reinforcement. So I think the previous two talks did a great job of talking about Markov decision processes. In this case, I'm thinking about a bandit case where the input, the state is just a prompt, and the action that we're going to take is the entire response. And basically, that's the Markov decision process that we're thinking about. And then you're going to have the reward, which is basically now you're going to get rewarded for every response, basically based on the actions that we're going to take. And we think about the expected reward. I'm just defining it as an advantage function, but we really don't have to do that. And then, because the second term is a constant, and then we define a drift from the base policy, which is we're defining as a KL divergence between the policy pi and the base policy p. And then we're going to define this RL objective, which is the expected reward minus beta times KL divergence. I think we've seen this variant of this a few times today. And so this is actually a linear in pi, the first term, and the second term is strongly convex in pi. It has a unique solution. We can actually solve it in closed form, and I think we've seen this kind of solution a couple of times today as well. And so, okay, are we done? I think the previous talk, we were told that we are not done because there is a partition function. We can't really sample from this distribution, right? But I think let's but really what we want to do is we want to sample from this distribution. So that's basically, I'm going to call it the posterior, but it was called the Gibbs distribution in the last talk. So our goal is to sample from this posterior distribution. And if we can sample from this posterior distribution, we're going to be done. Okay. Now, so I'm just going to rewrite it in terms of Q. So this is now going to be just P times Q to some power 1 over beta. We had dealt with these kind of distributions. We called them tilted mismatch distributions. They show up in basically identifying our error exponents. In channel coding, they also show up in kind of mismatch guesswork solutions as well. So they have been kind of studied in information theory as well. So just to do a sanity check, if you send this beta to infinity, we're going to get back the base distribution. And if the beta is 0, this is going to become a deterministic distribution, and you're just going to output the outcome that has the highest reward. So basically, in other words, if there is no KL regularization, this is going to degenerate to the highest reward outcome. And then if you have infinite KL regularization, you're going to just stay at the base model. Okay. So since I'm an information theorist, I have to show you this probability simplex. So we're going to now think about a very, very simple language model. This very simple language model is going to generate zeros, ones, and twos. So it has like three outcomes. And this is the probability distribution over those three outcomes. And we're going to only generate 0, 1, or 2, and then we're going to stop. So it's very, very simple in that sense. And I'm going to define the function q as following. Basically, it's given by this kind of stochastic vector. And then we are now going to try to visualize basically the set of solutions to the alignment problem for this extremely simple language model and see what we observe. So this is the probability simplex. Basically, this is so any ternary distribution can be mapped to the probability simplex. This is the distribution that always generates zeros. This is the distribution that always generates ones, and this is the distribution that always generates twos. And any other distribution is going to be a point on this simplex. And this is what we're going to get. Basically, this is now distribution P. This is the distribution Q. And the set of solutions to the alignment problem is going to be this exponential family of distributions. So it's an exponential family of distributions. And basically, I'm just also showing you for like a particular constant, a reward contour. So as I said, the reward is a linear function of pi. So we see that it's a line here. And the KL contour, it's a strongly convex function. So the contour is going to be a kind of a convex function. And so the intersection of the two is going to be the distribution, the solution to the kind of alignment problem. Okay. Now, one thing we want to see again is that if you keep aligning, basically with letting beta go to 0, what happens is that you're going to degenerate. And even in this very simple example, we're going to get a degenerate distribution. So generally, we want to make sure that we do the search in a KL ball around the original distribution. And I'm going to talk about what that value of KL is going to be. Okay. Now, one thing that we didn't talk about yet is that where does this kind of alignment distribution Q come from, or like where does this reward come from? So in this case, it can be a classifier for safety, for example, in terms of safety, or it can be trained using a Bradley-Terry model. I think we can skip this part. I think it was discussed. But also, reward really doesn't have to be trained or differentiable. Sometimes you may want to, for example, use response length as a reward. It can be, basically, it can be any function. So this is the Bradley-Terry model. I think it was talked about quite a bit, so I'm going to try to skip these parts a bit. So it basically determines that the probability that response y2 is preferred over y1 is going to be a sigmoid function of reward of x and y2 minus reward of x and y1. And then generally, when we do reward modeling using the Bradley-Terry model, we take basically we take the log of this model. We train over this is the preference data set of kind of prompt preferred and unpreferred response pairs, and we get a reward function. And then, as I said, we're going to try to do a KL-regularized reinforcement learning, which is basically this expected reward minus KL divergence again. Yes.
Has anyone tried to actually check how much of a model mismatch is there between human collected data with this Bradley-Terry model? Like you can try to just fit the best, like Bradley-Terry model to your preference data, and then you can check, like you can try to check, like if the fit of the model is like.
Yeah, so that's a very good question, right? So I think, like it depends, right? In cases when we're talking about like safety, like there is anthropic data set for helpfulness and harmlessness, and when you train a Bradley-Terry model, then you can have the tests split of the data and then go check whether it agrees with the test split. Generally, you don't get better than 75% accuracy on the test split. So it's extremely noisy. Okay. Now, I think you can basically plug solution to the alignment problem into the Bradley-Terry model. I think I don't need to convince you that then that leads to DPO. And there is many more algorithms. Like you can basically take any function of the reward model that you get and define a different kind of preference optimizations. I think at this point, it's safe to say that there is at least one paper on this coming on arXiv every day. So many more. Okay, so how do they differ? I think I want to talk a little bit about like the differences between these kinds of algorithms. So some of them are training time solutions like DPO and PPO. What does that mean? It means that now you're getting a new model. So it's plug-in. You can basically take your old model out and then put in the new model and then just deploy it very easy. That's why they're widely used, very easy to deploy. Some of them are inference-time solutions like best of n. So it's now you need to do extra work at inference time. So it's, as we see, it's modular, it's easier to adapt, but then it's from an infrastructure perspective, it's harder to serve to the users. Then they differ in terms of solvers. So DPO requires you to just do supervised learning, so it's much easier to do. Whereas the policy optimization generally requires rollout. So there is basically, again, different type of infrastructure that's required to be able to solve those kinds of problems. In terms of reward, we talked about basically training a reward model, but then reward could be also coming from AI feedback. There is like a lot of papers on this versus human preferences. You can do explicit reward modeling versus implicit reward modeling through DPO. And then in terms of training, they could be online kind of RL solutions via model rollouts, or they could be offline. But I think one thing that's common between all of these kinds of solutions is that all of these methods roughly are solving a KL-regularized reinforcement learning problem. So then it's natural to ask, what's the role of this KL-regularized? Can we change it? Like, is anything specific to KL? Like, why are we using a KL-regularizer? I think there are some papers that have tried to change that with little success. And I'm going to try to tell you why that is the case. So again, assume this very simple logistic language model that I just defined. Let's say, think about this like ternary language model. Now, you can do supervised fine-tuning. So basically, supervised fine-tuning is the task of the basically stage before reward modeling, where you had this cross entropy loss on some data set, and then you're training the model on cross entropy loss. And let's call the outcome of that stage theta of SFT. Then we do KL-regularized reinforcement learning. So we do KL-regularized reinforcement learning. What we are doing is that we are saying, OK, let's do regularization of pi theta to pi SFT. And then we're going to add the reward optimization objective, which is basically the expected reward. And that's going to be the solution to this kind of two-stage problem. So there is a two-stage training. You did SFT first, and then after SFT, we are going to do the kind of the KL-regularized reinforcement learning. Or we could do multitasking between SFT and reward optimization, I think, which is basically to take this same objective and do a mix of the two kind of objectives and do multitasking between the two. It turns out that the solution is exactly the same for this kind of very simple logistic language model. So in a sense, the role of this KL-regularizer is that it's enabling you to do multitasking between these two objectives, but in a modular manner. Now, you don't have to really care about what the reward optimization is going to look like when you're doing your supervised fine-tuning. You can just do your cross-entropy loss, whatever solution you're going to get. You can basically now, through this KL-regularizer, you're going to get the exact same solution. Or in a way, you're really losing nothing by doing this two-step process rather than just doing everything all at the same time. OK. Now, with that, I'm going to define YAM, which stands for yet another alignment model. So now we're going to actually change this kind of the view of reinforcement learning. And rather than this bandit Markov decision process, we're going to define a token-wise Markov decision process, where we're going to define the prompt plus every token that has been decoded so far as our state. And then the action is going to be the next token that we're going to be trying to decode. And then for reward, we're going to give a 0 reward in every intermediate stage until we actually fully decode the sequence. We get end of sequence. And then we're going to evaluate whatever we decoded through the reward function, and that's going to be the reward that we're going to get. Now we're going to define the value function. I think I don't need to define this. It has been already talked about. And which is basically the expected reward that you're going to get when you continue decoding from a given kind of state. The important piece is that we're going to define the value function with respect to the base policy. And we're going to define advantage function, which is now I'm going to start perturbing the decoding policy from p to pi. And then I'm going to try to see what's the impact of that on the expected reward. So basically, I'm just going one step ahead, and that's I'm going to look at the difference between the value, expected value of where I'm going to end up versus the expected value of if I just continue decoding from the base policy. And now I'm going to define drift. Again, it's a KL divergence, but it's a token-wise KL divergence. Just basically the KL divergence between the distribution that's induced on the next token. So this is now just one token, given the state versus the base distribution. Now, basically, if pi is equal to p, both advantage and drift are going to be 0. So we're going to try to make advantage positive, but then we're going to also have some drift. So then that's going to be the trade-off that we're going to try to explore. And we're going to define the RL objective as just advantage minus beta times drift. So very similar to how it was defined at the sequence level. But now we defined a new kind of Markov decision process at the token level. Turns out that we can solve the exact same problem with the exact same math, and this is what we're going to get. Basically, now the solution is going to be the base distribution exponentially tilted now with the value function for the reward rather than the reward function. Now, again, you need to normalize this distribution, but we can normalize this distribution now because basically the partition function has to be computed only on the next token distribution. So that's like, let's say, if the alphabet size is 10,000 or even 200,000, this is a sum that you can actually do very quickly and efficiently. So we can now sample from this distribution, which is something that we couldn't do for the sequence level MVP. Any questions? Okay, now I think we're going to do the simplest things that you can think about is like, how do we learn this value function? We're just going to do it through the policy iteration. And basically, it's very similar to how DQN was trained. Okay, I just jumped ahead of myself. That's not what we're going to do. So how are we going to solve this, basically train this value function? Because basically, we don't have V star, right? So basically, how should we set up the target for training this value function and distilling it into a new model? By the way, this value function is just another transformer. So you just take another transformer, very similar to how you train a reward function. It's the exact same shape as a reward function. And it's just basically now generating a distribution over the tokens. So a simple thing that you can do is to say that, OK, I'm going to just draw one sample from my base distribution. I'm going to basically decode token by token, go all the way to the end, and then see what reward I get. And I'm going to associate that reward to the value function for every intermediate stage. So given that this reward that I got is on policy with respect to P. So this is an unbiased estimator for the V star for every intermediate stage of decoding. And I'm going to use that as the target for decoding, for training this value function. And it turns out that this was already done in 2021 in a NACL paper by Yang and Klein in UC Berkeley. And it actually works well. So I think our contribution here is to show that what they had done for control text generation is actually solving a KL-regularized reinforcement learning problem. So I think the takeaway is that the NLP community was way ahead of the ML community, and we are just reinventing the wheel. Okay, so basically, this is a very, very, very simple theorem. So, yeah. Okay, now that we know that what we are training is actually a value function, we can do it differently. We can basically, we can go ahead and do a kind of policy iteration, and very similar to how Q-learning is done. Did I kill this? I think so. Yeah, okay. We are back online. So very similar to how Q-learning is done. Basically, we can now get the target to come from the Bellman identity, and then we can train this value function this way. And this is, we're going to call this the CDQ variant. And this was the name of the algorithm then that Kevin Yang proposed was called fudge. I'm just going to call it CD fudge, just for the sake of comparison with kind of other methods. Okay, now that we trained the value function, how are we going to sample from our language model? So the sampling is going to be extremely simple. We're going to just follow this theorem. We're going to basically take logits from the base language model. We're going to take logits from the value function, and we're going to mix them and then take it through a sigmoid function and then sample from that distribution, right? So yes, so now we are going to use V theta, right? So V star is basically the aspirational value function, but we're going to use whatever we learned, yes. Now, so let's go through an example here. Will this paper get accepted? This paper will be. And then let's say there are like 4 next tokens that are possible, and the language model is going to have some likelihood function on these possible outcomes. But then now, let's say our goal is the value function here is sentiment score. We want positive sentiment. So we're going to get also a sentiment scorer for every single one of these kind of continuations. And then we're going to mix them, and then we're going to now get a new distribution. We're going to sample from that distribution. That makes it more likely to kind of accept liked versus the other ones that have neutral or negative sentiment. Okay, now one thing that this does, oh, sorry.
Sorry, no, you mentioned earlier, I just wanted to make sure for all this, we're still needing to have like an automatic reward function, right? Like a transformer that can like give you the reward. You just put it.
Yeah, so we trained one, right? We trained this value function.
Okay. So it's not like if you want to do like RLHF.
Uh-huh. So we are basically solving an RLHF problem in a totally different way, right? So it's basically we're solving an RLHF problem, but with a totally different way, kind of solution. Very similar to how DPO is solving an RLHF problem, but in a very, very different manner.
Sorry, that makes sense.
Okay, that's a good question. Yes.
How do you tune the harvester beat?
So okay, so I think in practice you have to just do kind of human evaluations, maybe have some kind of metrics, et cetera, et cetera. But generally, beta, again, very similar to how the original RLHF is done, is that this is going to be a knob for you to remain close to your base model, or like basically optimize your reward more and more.
Is there a clear way to describe how this optimal policy differ from the PPO optimal policy?
So that's a very good question. I don't know. But I think some people have actually, some Maryland researchers have started looking into this, and they have also tried to close the gap between kind of this framework, the token-wise framework versus the sequence level framework. But what we're going to do is we're going to actually evaluate everything at sequence level and compare how much degradation you may be able to get from this objective.
Thank you.
Okay. So now this opens the door for some other things that you wouldn't be able to do with DPO or PPO. Now we're going to do block-wise sampling and block-wise control through this kind of prefix scorer that we just learned. How are we going to do that? Basically, if you think about best of n is doing sequence level control, right? You're generating a sequence n times, and then you're picking the best one. Now, what we're going to do is we're going to generate the n blocks. So this should be n of length m. So now we're going to only decode m tokens. But now we're going to use our value function as the signal for choosing which block to keep and then continue decoding from there. So it's going to be greedy with respect to the value function. But we are now only going to do it on a block of length m. So that's going to be kind of it's going to reduce the latency quite a lot, because now we're only doing this for block of length m, but the throughput still is affected by a factor of n. Now, to just give you an example, will this paper get accepted, this paper? Now, let's say m is 4, so we generate 4 tokens. Will be liked by, we'll receive diverging reviews, maybe liked by, and so on. And then now we're going to look at the sentiment prefix score. And this gets the highest score, so we're going to keep this continuation, reject the other 3, and then continue. Okay. Now, the key advantage of doing this is that it's going to limit the user-facing latency to just this decoding of a single block. And I'm going to talk about why this is going to actually make a large effective n practically feasible. So the effective n is going to be much, much, much larger than the n that we choose, and it's going to actually be exponential in the number of blocks that we're going to be decoding subsequently. Okay, now we trained a bunch of alignment methods, including YAM. And how do we evaluate? Yes.
Like, it might be the case that you choose like a fragment of the continuation that indeed is not like a very probable continuation. Maybe you sample something that is kind of like rare, and maybe by doing this, sometimes you can push the response
that is true, but like if your m is large enough, then that is also becoming unlikely to happen. But if your m is like 2 tokens, then that's very likely to happen, right?
Is there a way of controlling for that too, like the quality of the thing that you pick in terms of?
So in the end, right, so if, for example, let's say if m is 1 token, and if your n is 1 million, you're effectively going to see every single token, and you're going to be greedy on the next token with respect to value function. It's going to totally degenerate your model, right? So I think these are parameters to play around with, and we're going to try to come back to like some ways of thinking about that as well. So, yes.
So if I understood correctly, like in the previous slide, so for this segment, you're only using the prefix to
Yeah.
the value.
We don't care about the probability.
Okay. So you generate using the language, the model P,
Yeah.
then you are evaluating using the value function. Which one you keep, and then generate again with value.
Yeah. But you could, for example, say to also to your point, you could take p times e to the 1 over some beta v as your acceptance rule, and you can change that. And so it could be useful in some scenarios, but we're going to just keep it as this. Yes. Okay. Now, how do we evaluate alignment methods? So I think the gold standard is human evaluation. The silver standard is if you have some automated evals that are correlated with human judgment that you can actually use to evaluate your models. Generally, these things take time. Like human evaluation may take weeks. Auto evals may take days. So is there something that we can do for engineers to actually understand whether or not we're making progress? So we're going to do a very, very, very simple evaluation. And the simple evaluation that we're going to keep seeing on these slides is going to be the x-axis is the KL divergence between the new model and the old model. So we want this to be low. And the y-axis is what's called the win rate against the base model. So I'm mathematically defining it here. It's basically now you're going to draw two samples, one from the base model, one from the new model. And then we're going to have a judge to say which one is better. I'm putting an R here, but generally we don't use the same reward that we use for training. So we're going to try to use a different reward. Maybe it's a kind of you prompt Gemini to say which one is better, or you have a different kind of set of data that you use for reward modeling here. And ideally, we want to go all the way up without paying any KL penalty, but that's not possible. So we're going to actually see some kind of results on what may be possible. But that's basically the picture, and the method that dominates any other method is going to be desirable in this picture. Now, with this, the first question is how do we compute KL divergence? Okay. So why are we limiting to 8? Again, remember, we wanted to remain to a close KL contour of the base model, because otherwise we're going to degenerate. And I'm going to actually try to convince you why 8 is a reasonable number to consider here. Okay, so how do we estimate KL divergence? How much time do I have? Okay. So when you have a new policy, pi, and an old policy, p, estimating KL divergence, you can take the log likelihood ratio. Like you can basically sample from pi and take the log likelihood ratio of a response under pi and p, and that's going to be an unbiased estimate of the KL divergence between the two distributions. But we don't have the logics of best of n or blockwise controlled decoding, so how can we actually estimate KL divergence for these kinds of models? It turns out that there is a magical formula that says that the KL divergence between best of n distribution and the base model is log n minus 1 over n. And remarkably, this doesn't depend on anything. It only depends on n. Doesn't depend on the base distribution, doesn't depend on the prompt, doesn't depend on the distribution of our prompts, doesn't depend on the base language model and anything else. So then I think it's logical to ask whether this formula is correct. And it turns out that it's incorrect. So we can actually now do a simpler language model. This is just a binary language model, 0 and 1. And 1 is going to be the preferred outcome. So 1 gets a reward of 1. 0 gets a reward of 0. We can compute in closed form what the best of n distribution is going to be. And we can actually compute the KL divergence in closed form. And then we can plot it. And this is the KL divergence that you get. And this is what the formula is going to tell you. And basically, there is a gap between the two.
Was that like an empirical observation from previous works, or like this claim?
No, it was claimed that it can be proved that this is true.
But the proof was in the paper.
then the proof is it's claimed that it's in the appendix of another paper, and then in the appendix of another paper you go and it's stated as a fact. And then there is a blog post that claims that this is true. Yes.
Just trying to understand the intuition. So I guess the intuition behind it is that you take the max of n random variables.
So yeah, I'm going to come back to this. This is actually not a bad formula. It's actually very close to truth. But there are some assumptions that are never stated anywhere. Okay, so it turns out that this is actually an upper bound on the KL divergence. And you can prove it. And then as long as the probability of your kind of highest reward outcome, but basically the probability of the outcome that you select through best of n is not high, or like n times that is small, then this is actually a very remarkably good kind of approximation to the KL divergence. And I think more recently, Youssef from IBM has showed that this is a form of strong data processing inequality. So if you're interested in the theoretical connections, he has a beautiful paper. Okay, so you can do better. So we came up with a different estimator that basically does much better than the original estimator. But really, in most practical scenarios, especially in chat applications, the kind of the KL approximation is quite close to reality. Okay. Now, how do we estimate win rate? So we talked about KL divergence, but let's talk about also win rate. Yes.
Okay, sorry, just a quick question. So is that formula is an unbiased estimator, or?
So this is not this is an unbiased. This is not an unbiased estimator for KL. If you take the expected value of this, so we have a conjecture that the expectation of this formula is an upper bound on KL. I wasted 3 weeks of my life trying to prove that, and I couldn't. So it's an open problem, but it seems simple enough. But yeah. The conjecture is that this, basically, if you take the expected value of this formula, that's an upper bound on actual KL divergence.
Even tighter bound.
So it's empirically, I've observed that, like I've simulated many things, and it's empirically true, but I couldn't prove it. Now, how do we estimate win rate for best of n? So it turns out, so you can actually compute so there is, you can come up with analytical formulas for win rate. But one kind of intuitively, we can think about win rate for best of n as follows. Draw n+1 outcomes from your base model, and then randomly choose one of them to be associated with the base model, and then the other n to be associated with your best of n model, okay? And then out of the other outcomes, pick the best, and then compare it with the one that you left for the base model. And then the probability that the base model is going to win is just going to be 1/n+1, right? So the probability that that's the highest reward is going to be just 1/n+1. So the win rate of this best of n model with respect to the base model is almost n/n+1. So there are assumptions here because now you don't have to hit the same thing twice, etc. But then those are the same assumptions, the same kind of approximation limits that you would need for the KL formula to be correct. And in that limit, you can actually, now you have analytical formulas for win rate versus KL divergence. Where did that go? And that's the analytical formula. So you basically, now you can see that you can reach a very high win rate with a very extremely small KL divergence. So that's possible with best of n. Now we didn't even go to KL-regularized reinforcement learning. You should even be able to do even better. So there is no reason to actually consider KL divergences higher than these numbers, right? Now there is caveats here. And the biggest one is that here we're looking at an idealized setting where we're ignoring noise, we're ignoring generalization, and so on and so forth. So you're not going to be able to reach one ever, etc. But kind of that's the picture to keep in mind. Okay, now I just want to connect with this plot we already saw twice in two different talks. This is from the scaling laws of reward model optimization problem. Now, I think one thing to keep in mind is that we're not really interested in those high KL values. So that's actually reward hacking regime. And so I think one question that I don't know the answer to is that, is reward over optimization, is it really a problem? I'm empirically think that it's not, but kind of I think that's a good question to try to think about. Okay, so with that, let's actually see some results. So we are looking at, so this is the anthropic helpfulness and harmlessness data set. We're looking at win rate versus KL. And here we're looking at different methods, including IPO, DPO, and PPO, and including the token-wise as well as the block-wise variants of control decoding, and best of n. One thing that we see here is that best of n comes on top. I think a lot of people are embarrassed to report best of n because now you have a new method and then you compare it against best of n and then best of n comes on top. And in fact, one of our ICML reviewers said, oh, you're claiming best of n is the best? That's nonsense. And I'm going to, in the rest of the talk, like we have 5 minutes, I will try to convince you that actually best of n is almost optimal. The only reason that we don't do best of n is the kind of computational issues. Otherwise, it's actually close to optimal. And another thing that we see is that the block-wise variants of control decoding are actually very good contenders for this alignment problem. They are much closer to best of n. And all of these token-wise control methods are horrible, and they're horrible in the same way, including ours. Yes. So okay, so you're varying n, right? So for different values of n, you get higher KL divergence. So you go. So we can't really. It's impractical to try to continue this curve. Yes.
So for the clockwise ones that you talked about, like so roughly how much gain do you get in terms of like being able to preserve it?
So I think I have some numbers as well on that. Yeah. Yes.
Like with early stopping, the last two DPO.
Yes, DPO is with. Otherwise, it would have degenerated and would actually not even.
Are you applying the regularization and doing early stopping, or there's no regularization?
I think there is no regularization.
So it's just early stopping.
Yeah, but I think as it was mentioned in the previous talk, DPO is not as good as PPO even. So and all of them, like if you tune them, all methods are pretty much the same. So tuning is all you need. But there is a huge gap between what you can do and what you get with the token-wise methods. And I think that's something that I'm interested in closing that gap. I don't know how to close it. Okay. Now that, okay, so now you can actually do multiple rewards. So here I'm doing, so I think it was mentioned in the previous talk that preference data are generally correlated with length. So higher length data are generally correlated. So what happens is that if you do, let's say, helpfulness RLHF, then what happens is that you're also going to increase the length, verbosity of the responses. So the length of the generated response is going to go up. Now we're going to be able to also train a value function for length as well. And then we're going to also combine them to be able to kind of correct for length. One thing that we did that was interesting is that we took this value function, we applied it to a new model, a larger model that was not seen during training, and it did generalize, and it basically can, out of the box, give us good win rate versus KL trade-offs, similar to best of n, which was, I think this was surprising, to be honest. But they're from the same model family, so they're both Gemini models, different sizes, so the same kind of data for training. You can also use it with this control decoding and DPO. So generally, you can get, so I think this is not really visible, so you can get 1 to 2 orders of magnitude improvement in terms of the n that you need for the same trade-off point that you would get with best of n. So here, this is not even best of n, this is CD itself. And then when you combine it with DPO as your base model, you can actually get, like, be able to get to the same trade-off point with an n of 8. Yes?
Just to understand it clearly, instead of starting from the reference model, SFT model,
You're-
you're starting from the DPO model
Yeah.
and then doing the...
Yeah. And then it's very similar, like it also does generalize to the DPO model, right? So that's the interesting thing. Yes.
So is the win rate always measured against the base model?
It's always against the base model, yes.
But I wonder, maybe it's not the best metric we hope to look for, because it's possible that some decoding algorithm always wins over the base, but the distribution of reward is still very low because the base is not good.
That's a good point. Yeah, that's a good point. So that's a caveat of this kind of, we haven't done any other, like head-to-head kind of comparison, we haven't done.
Thank you.
Yes.
What's the computational complexity of the combined multi-level versus best of n?
So the kind of the complexity of decoding depends on n, right? So now we can, I think here I'm showing that you can get 4x improvement in terms of the required n if you combine a DPO-based model with kind of the CD. But then generally CD itself with respect to best of n gets you another factor of 10. So you can get, like, basically you can make it practical. 5 minutes? Yes.
Oh, sorry. I just wanted to clarify, which is possible. That's against the helpfulness and harmfulness.
So this is, okay. So this is against length, and so we combined helpfulness and harmfulness into one reward from the get-go. So that's like one reward, and the other reward is now length. Because basically, if you try to optimize helpfulness and harmfulness rewards, you're going to become more verbose. And then now we wanted to correct for that. And that's basically by training a multi-head kind of reward similar to the previous talk. One is the length, one is the other reward, and then you can basically just now combine the logits from the two different heads, the two different value function heads for the two different tasks.
So second plot, generalization to new model.
So this is, let's say you have a 2B model, you trained your value function for a 2B model, then you use it on a 9B model that you hadn't used. Basically, it's a value function of the 2B model, not the 9B model, but it does generalize to the 9B model. Or it's not the value function of the DPO model, but it does generalize to the DPO model. Okay. So basically, if you remember, when we're doing this kind of reward versus KL trade-offs, so the RLHF objective is expected reward minus KL. This is linear, this is strongly convex. For if I really want to find the best reward versus KL trade-offs, I should be solving the RLHF problem. So then the question is, why is best of n coming on top, right? Now, empirically, best of n is actually strikingly close. So this is, again, this is a simple one-step model, like the simple language model with different alphabet size and everything, and I have observed time and again that you're going to get very, very close to optimal curves from best of n. Now, we don't have time, but we actually proved this for this very simple model in a very toy setup that you can actually, it's basically, the best of n is asymptotically optimal. Now, I don't have time to define what the asymptotic sense is. Then the other question is, I think we are out of time, can we distill best of n into a new model? So if it's so good, can you actually distill it back into a new model? And that's actually, so I think that there have been 2 follow-up works that try to do that, and they see some improvement. Still don't close the gap with best of n, but there is some improvement there as well. So yeah, I think I don't have time to go to the practical kind of details of alignment, but alignment is hard. So I think the talk made it appear simple, but there is generally a lot of moving pieces, reward models, like the prompt sets that you need to use. Do I need to roll out my models? Can I live with the offline methods and so on? What happens to multilinguality? In a lot of the cases, the biggest gains come from data. So in reward modeling, you need actually good data to be able to do good reward modeling, or like you need to be able to choose the right prompt sets. So I think Ahmad talked about like these adversarial attacks. Those kinds of adversarial prompts could be useful for doing the RLHF, right? So these kinds of slices of the models. I'm going to skip these parts, like safety alignment is shallow. I don't have time to talk about them. But I want to talk about something that we were doing last night with Andre and Maddie on further understanding of DPO. Unfortunately, we couldn't solve the problem, so I have 2 empty slides. And let's end the talk with some takeaways. So always let's do best of n, like, because best of n is almost optimal. So I think it's tempting to start with the most shiny kind of version of the RLHF that's out there. But actually, let's start with best of n. It's much easier to debug. It's easier to inspect. And if best of n is not working, something is wrong. So I think let's start there. And then only then you can go and try the most fancy versions of RLHF. In chat problems, especially now, I think in some problems it may be okay to go above KL of 8. But in chat problems, KL above 8 is already in the overfitting regime. And always when you have high KLs, you have to inspect the outcomes for reward hacking. And I've seen papers reporting KL in the order of thousands. I don't even know what the responses would look like when you reach that levels, but that's definitely not useful outcomes. And yeah, these are the papers that I covered today. The slides for this talk and more, some speculative decoding and kind of general language model inference are in this link from a language model inference tutorial that I gave with Tirtha Suresh at ISIT. Thank you. And sorry for keeping you all so late. And thanks for not falling asleep. Sorry?
So alignment was solved at ISIT.
Yes.
For the multi-objective, where you're combining I think you said you're combining the heads from 2 different value functions. Is there a way to should train a new single value function on those 2 to implicitly combine them?
So we don't want to do that because generally you want to have that configurability, right? So generally it's actually desirable to have multiple value functions and be able to combine them. One thing that I didn't mention is that you can actually also make these as kind of LoRa heads on the base model and so on. So it's and train basically the value functions as a LoRa head on the base model.
So I guess I have a question. So somehow, why is that surprising? Why is it that surprising? Why do people find it that surprising that best of n is kind of like the upper bound? Because you're just trading off. At some point, you're just basically doing exhaustive search for a large n. You're basically just pulling over all possible. It's like you're sampling in a brute force manner.
So I don't know. I found it surprising to believe as well. So I think when we started comparing with best of n, I was trying to debug our method for a long time until we realized that, okay, no, everything is kind of dominated by best of n, and I was pretty sure that some of the baseline we have implemented correctly. So I don't know if it's not super obvious that in terms of reward versus KL trade-offs, best of n has to come on top because it's not even solving that problem. And all of the other methods are explicitly trying to optimize that kind of objective, right?
I think to answer your question, I think part of that is due to accuracy is a discrete metric rather than sort of like continuous measure of how the reward model is. Like for example, it's possible that like best of n outperforms the base model n out of n+1 times, but the reward never reaches the level such that accuracy is like it's correct rather than incorrect. But some RLHF methods, like let's say 20% of the time reaches that reward threshold, so its accuracy is 20% rather than best of n always is 0% accurate.
Just super quick. Is it clear that best of n and RLHF are even two algorithms in the same category? Like RLHF is like a training algorithm. Best of n is an inference algorithm. It's not clear that RLHF is better or worse than best of n. They're just somewhat different. And moreover, when we try to distill best of n, we find that a lot of the gains are lost by distillation that we don't see in inference time.
Yeah. So I think that is true, right? But then I think that the thing is that the best of n implicitly defines a distribution over outcomes. Now, whether or not it's learnable, I think that's a different question. So we don't know if you can actually learn it. Is it a capacity problem? Is it an optimization problem that we can't distill it?
I see, but it's proposing the optimization problem.
Yeah. But it is a distribution. We know that a distribution exists that has good reward KL trade-offs. We just don't know how to get it distilled into a language model.
I guess like related to that like in most recent like this the comment like is there a way to even in simpler setting thinking about like the capacity of like or like the achievable like in that you're doing rate versus scale things?
Yes, I don't know. I think it's an interesting question. I don't have a good setup for thinking about that problem, but I think it's a very worthwhile problem to explore.
Okay, let's thank Ahmad.